Okay, so I'm going to actually pop up the YouTube here before I get going. My channel playlists live. Old School Coding Part 2. Welcome, welcome, welcome. So in Part 1, we worked out this thing called a step. A step is, to use the 10-second elevator pitch, a step is a function to call and a parameter to pass it. And we set up a bunch of things around that, exercised through the development loop, and got something working. So the next thing I want to do is an expandable list of steps that can be executed. For example, if we have a rising edge on a signal, that rising edge causes a number of different people across the simulation, different objects across the simulation to wake up and do something. So this is essentially a static list that is going to grow in length. And in some simulations, it is possible to do static initialization of this list, but that presumes that you have everything all collected together and you're going to static initialize your whole simulation all at once. I think we can set things up eventually so that we can do static initialization, but I believe that it is more flexible to allow dynamic initialization as our first step. So we can say, add this to this list, add that to this list. So I am going to call this subs. So we're going to go subs.h and subs.c. And I trigger that off, and that triggers a build. And yeah, so at this point, you'll notice that when we reformatted, it was empty. Basically, indent really doesn't like it if you're empty. But other than that, we're okay. So subs.h, subs is a sequence, is a list of steps that can be extended or executed. So there is our one-line elevator pitch, 10-second pitch on what subs is. And now let's start building up this thing called subs. I am going to start by grabbing a bunch of comments from Step. First of all, we start with Step, and I'm going to go find all the places where there are braces like that. So the stuff that I'm going to need in subs, I'm going to need support.h, common support for, so we may have some common code in here. We're going to have post. Stubs post, stubs bist, stub bench, and we may have other code at the bottom. So there's our empty stuff. And now we're going to take these three lines and put our extern declarations in. So that's set up. So now, let's see, to make this actually compile, I need to put these in, and let's verify we're getting called. Yeah, print top and print end. So between streams, I actually went through and added some comments and checked it in and pushed it up to GitHub. So we are starting out here with no changes in Git yet. So now we need to modify the main function. So wherever we had step, we need subs. And now we should have a compare error. Haha, implicit declaration, because I need to have that. So now we are compiling, we are running, we are executing post, best, and bench inside stubs, which are doing nothing, and we're hooked up. So now as I add code, it will be tested on check-in. So what is stub? What is subs? Well, it's going to be a structure. We're going to follow that same convention of having a subs, which is an array of 1, and a p subs, which is just a pointer. So we can pass around pointers to these. We can store pointers. We can declare that our parameter is a subs rather than a p subs to say I really need 1. Now inside it, what are we going to have? It's going to be a list of subscriptions. So this is a p step list. Okay. And the list has a capacity. I'm just going to do int. And it has a length. So so it may have a ability to store 20 steps, but only the first 16 of them are valid. We will probably need more things as time goes by. So I am going to need to have a way of initializing these, because right now, all 3 of these being 0, that's good. But if somebody were to declare a subs that's not at global scope, it's going to be random memory. So they would have to remember to clear it out. And I think the easiest way to do that is to have a subs init. So let's build an initialization function. And I am going to also print top and print end inside this function. This is a habit that I had forgotten that I was in, but as I'm swinging back into doing this development, I'm remembering more and more about how I did things. And new functions, yeah, printing when you get in to verify you're getting in, pretty much standard with what I was doing. So subs init says subs s, it says unknown type subs. Well, hell. This includes subs.h, which includes this type def, which includes that. Oh, I probably got a build log from before everything was saved. Okay, so pstep. Subs needs to know what a step is. So pound include step.h. S is not used yet. That's fine. There's another thing I want to do here. We'll see that in a moment. Let's initialize this. S_list is equal to null. Cap is equal to 0. And len is equal to 0. Much better. So once we have this established, subs has invariants that I want to maintain. I want to be sure that certain things are always true. And this wasn't worth checking on step, but I think on subs it's going to be important. For instance, if I'm doing a subs in var, like that, if somebody says subs in var, I'm going to do an assertion failure if it's a null pointer or if any one of a number of conditions are true. Now, I'm going to require that cap is greater than or equal to len. And if s0 cap is greater than 0, then I'm going to require s0 list is not null. So basically, if we have non-zero capacity, we need a list to put it in, and if we have a length, then our capacity needs to exceed that length. Real simple. I'm going to make that an external function so that other people can call it. I'll put it up at the top, because when people are looking at this list line to know what functions are there, I'm going to start right off with, if you call this, it's going to do an assertion failure if this isn't a valid subs. I want people to be aware of that when they start working with the API. Next thing you do is initialize it. So that works. Subs post, I am going to put in a quick check. I'm going to say subs s, I'm going to leave it uninitialized. And then I'm going to say subs init s. So no matter what garbage s gets here, this is going to make it valid. And I'm not going to assume that subs init does an invariant check, but that's good that it does. We need to start writing some tests here. Well, we have some stuff we can use. In support.h, I have this assert EQ integer that we worked up before. So when we come out of initialization, I'm going to assert that s arrow, it's expected then observed. I'm going to assert that 0 is equal to s len. That's the only thing I'm going to require out of init is length is 0. This will allow me in the future to maybe subs init gives us an initial short list, for example. Go to check something really quick here. Yes, okay. Wanted to make sure I had audio. So in the future, I could allocate some memory inside subs init and put it in list and set capacity. So what's the next thing we want to do? Well, built-in self-test. I'm not going to assume that post worked, so we're going to include this in the built-in self-test. We've already verified that these guys can get called, so I can take out the macros. Okay, so there we go. So BIST is going to get one and verify it, and Bench is going to get one and do something with it. Next thing is we want to be able to append to the subscription list. I'm doing uppercase, I'm doing lowercase, I don't know what I'm doing here. So in some places, it might be useful to use uppercase for this, so subs in uppercase or subs in var and so on. But that's a habit I got into much, much later. So we'll stick with the 1990s style here. So we are lower snake case for our function names. Having our types with uppercase is not common. Back then it would have been type def ... subs. This would have been, let's see, a classic version of this, like I actually would have typed it back then, would have been subs s, subs p, and subs a. Subs a for subs array. However, this isn't such a big departure to use capitalization like this and a prefix p. I was violently against this prefixing because it is a variant of Hungarian notation that removes all of the useful things in Hungarian notation in favor of useless things. I don't need you to prefix your integer variable with an I. I can tell it's an integer. I need you to have if you're using Hungarian, I need your names to represent what it's used for, not the data type storage. But prefix P, so common. Anyway, it's compact. It's a reasonable way of doing notation, so we'll go with it. Anyway, so our next function is going to be extern void subs add. And we're going to say add a, if I demand that I am passed a step here, I'm going to be copying a step structure. What I can do instead is I can say this is a step FP and a step AP being passed in. And that says add an entry to the subscription list. It says call this function with this parameter. Okay. So first off, we want to make subs bigger, and then we want to write something at the end. I believe this is the only method where we make subs bigger, so I'm going to start by doing it in line here. We may move it out to another function later. Explicitly going to call invar at the top of subs add because we are going to depend strongly on matching the invariants. For instance, the invariant that says capacity will never be less than len, and if capacity greater than 0, we have a list. So if len is equal to capacity, then we want to reallocate with a larger capacity. So I'm going to say cap equal to, if cap is less than 8, I'm going to say 8, otherwise I'm going to do twice cap. So we'll continually double our capacity. That's a strategy that works out well for expanding things. If we start getting huge things, we may limit how much we expand, but each time you expand this, you're going to copy all the content. If you double it every time, it means your amortized cost of copying the content is still bounded. Okay, I always parenthesize the thing you're passing to size of. Pause on that for a moment. In C99, size of looks like a function or a macro. It's not, it's actually an operator. So the question becomes, what is its parameter? And you actually can legally write size of list, and that does what you think, and if list sub 0 is the parameter. But if you were putting a type, you could say size of star p size of care. Oh, I have a cat who wants some attention. Hold on. So the question is, almost all of the time when you use size of, you're going to be saying size of and then left paren, type right paren. So size of, at that point, the parameter of size of is a cast. And it's just the cast operator, just the thing in parentheses. But if you're taking the size of a variable or piece of storage, you don't need the parens around it. I think that's confusing. It's confusing when I read it. So I always parenthesize my parameter to size of. Oh, funny little story on the distinction of whether size of is a function or a macro or an operator. There was quite the discussion at Sun back when I was a young engineer there over basically code formatting, which is why I use indent. Some people were very picky about code formatting. If you had the wrong indentation, or you had a blank in the wrong place, or you missed a blank in the right place, if you didn't have a blank after a comma, you could get changes that you proposed to the operating system, to SunOS, would be rejected until you fixed those formatting errors. And sometimes you had to go through and do a lot of editing. What do you want to see? I think she wants down again. She just wanted to say hi. What? No, do not crawl inside the computer. My computer is sitting down in front of the normal hutch it lives in with all the panels off, desperately trying to stay cool because when the power supply starts getting warm, it cranks up its fan, and currently its fan is not working well and it makes a loud noise. Anyway, so it's open to cats. So what we're doing here is size of list sub 0. So we're going to take list, and we're going to pass it to realloc, and realloc is its second parameter, takes a number of bytes. So it's the capacity times the size of the first entry in the list. And realloc has some special cases it handles. So for instance, if list is null, it'll allocate new memory. If size is 0, then it will free whatever memory it allocated. And if list is not, if neither of those is true, it will look at the actual thing that was allocated, which may be bigger than you ask. If you say allocate me 5 bytes, typically the library will allocate more than 5 bytes to you. And if you say reallocate to 6, it'll look at it and say, we actually allocated 16 bytes for you, so we don't need to do anything. It'll just update its bookkeeping. But if it has to allocate fresh memory, it does copy into the new one. And I believe it zero fills the rest of it, but I'm not going to count on it. So we're going to make this copy. We know that if the first n entries of list were valid, then the first n entries of copy will have those same n things. And if it did the copy, it then frees list after producing copy. Now, the compiler will warn us if we say, I'll show you, list. This is a really common thing we used to say. And GCC, it's got a few warnings in there. Oh, right. I would have to turn on some more levels of pedantic to get this. But at higher warning levels, GCC will warn us that if realloc fails, then it will return a null into list. And we could detect that like this, and that would fail. But if we wanted to recover from it, we've now lost our original list pointer, which hasn't been freed. Okay, we had a pointer to like 100 million things. We tried to reallocate to 200 million, and it failed. We've lost our pointer to what we used to own. So void star copy. And I am going to say assert copy. Able to realloc %p to new size, or to %d entries. And that's void star list and cap. Like that. I'm going to clear up the compiler warnings at this point. Subs init needs to be lowercase there. There we go. And I see over there that we are calling subs init 3 times, so we can get rid of those. We're calling it in the right places. We're all set. So the only thing the compiler warning mechanism will parse is the benchmarking results from step. Yay! So if we got back a copy, we're going to say list equals copy. So we have the list. I'm going to go back at s arrow list equals list and s arrow cap equals cap. Now at this point, we haven't changed anything else. So we can do a subs in var of s again. So once we have rewritten the list and the capacity, our invariants should still hold. Okay. Now we get down here and I can say len plus equals 1, assert len less than or equal to cap. After expansion, incremented cap %d not big enough to expand to %d items. Cap len. Now you may be asking why I'm writing these particular assertions, and this is because this is the kind of error that I have made in the past, and I don't particularly want to spend an hour trying to debug that I forgot to do something, like increment cap. Like for instance, if I set the new cap here in the realit call and didn't actually assign it anywhere. So now I can write s arrow len, len minus 1. So let's say int into, actually, certain len is less than cap. So here the len is still the old len. So eventually we're going to say s arrow len equals to len plus 1 and subs in var s. S arrow len, remember S is a subs, okay? So I am writing to the wrong thing. List arrow len. Now list, we go back to here. List is a pointer to a step. So list arrow len dot fp is equal to fp and dot ap is equal to ap. Okay. So then we can, having filled in len, we can now increment the length in the subs area, and that's now incremented across this entry, which is now valid. Of course, I could also say len is equal to step.h. This macro well, I would want to initialize it, so I'd say step s step is equal to step init of fp ap. But that's kind of crazy. The main reason for the step init function is to wrap everything up through casts. So it's kind of overkill to use that to write into a local structure and then do a structure copy to set it up in list when we could just do this. Although it might be nice to have a step setup function of some sort that allows me to do what I was about to do there. Don't know. Don't think it'll happen often enough. If we end up writing this code a lot, I will do something to package it up. So now we have the ability to add an assignment to a list. How does that change the invariant? Well, if cap is greater than 0, then we assert list. If len is greater than 0, I want to assert that each step is valid. And what I really want is a step invar of, well, step doesn't, the step functions don't tend to take that. Okay, do this. Step invar is going to want to be passed a pointer. This would be s arrow list plus I. But now we need step invar. Checks invariance on the step. Now I could have just wrote an assertion that FP was not null, but I think it's more clear because we've got an array of invariants, or array of steps, to say each step is matching its invariant. And again, I'm going to put the step invariant up at the top. And that's all I'm going to do. I'm not going to assert anything all about the AP. I can't actually dive through FP and see if it's a valid function pointer. So we can just do that. Now I'm noticing that suddenly I'm getting 18 nanoseconds per RTCNS call. I thought that was lower on the final run I'd done before. No, that's right. There it is, 2.928. I think what I'm going to do, now that I look at this, we've got two benchmarks outputting in different ways. I like the first way better. I don't really need to know the file name and line number of my benchmarks. So that's how I'm going to report benchmark changes. So step bench Oh, having multiple things called step bench is a bad idea. I didn't even notice that. I'll call it bench step. So this is the bench step. That's step bench. Why does it say max reps undeclared? Because I have to peel that off. DT is the actual result. Got it. So now over here we have benchmark results, 18 nanoseconds per RTCNS call and 3 nanoseconds per bench step call. And let's make this a little more honest. I am passing in a step. There are going to be 4 step runs. Let's do that. So this is actually 0.732 nanoseconds per step. Remember I said that we'd have important and interesting things that happen faster than a nanosecond, but there weren't going to be many of them. This is probably the only one. So this is a bench run call, a step run. So we're going to do a step run call of 3 more step run calls. Now, because we're using step elapsed to do all of our other testing will be a step run call that calls your thing. So for those, we can subtract out this 0.731 nanoseconds per call as the step run overhead, and the remainder will be what we charge to the actual thing being tested, if we want to do that. Bear in mind that overhead for the call to step run may be interleaved. We may be getting multiple things done at once in this CPU. So I hesitate to try to subtract out an overhead. So what we'll do is, I think I'm going to set the limits based on a step run of this function needs to complete faster than this often. Anyway, so that was a change to step. So we added the step invar, we set up the subs invar, we've set up subs add, and now I want to write a test that includes a subs add. What I'm going to do is a subs fn1, and it's going to require an argument pointer. Again, let's give it a pointer to an integer. Int subs arg1 equal to 1, 2, 3. Okay, so we got that. We're going to need subs arg declared and defined. So void subs arg, it takes an int star. And it's going to do what we did before, so plus plus star IP. We're going to bump a counter to say we've been here. And this is going to give us a casting problem. Well, not yet, because I need to write subs fn1, not subs arg. So now we have this basic thing here that we want to pass around to service functions, pointers to functions of various types. So yeah, we need something like StepAt inside subs.h for subs add. So pound define subs add SFPAP is subs add sub n. I'm not going to change S. S has to be the right type. However, FP does not. Okay, so now we go down here, and there's our new add function. We get a macro, and that is working. Let's make sure this is here. Yep, we're getting there. Now at the end of subs add, we do an invar, so we're verifying the invariant, but we're not actually calling it yet. Okay, so do we want to do a couple of these? Yeah, let's do FM 1, 2, and 3. And I'm doing all this in post. This post is going to be a little bit bigger than the other ones. Okay. Same strategies I used before, though. I'm going to increment by 1, 10, and 100. Redefinition of FN1, right. Okay, that compiles and runs. Now for post, we are now going to do the assertions. This is looking a lot like the BIST of assertions, except instead of having a function that does the calls, we have a list that we're building with this subs add. How would I call this? Same thing. Okay, these are step args become subs arg. Okay, so comparison failed. Sub arg 0 is equal to start val plus 1 is failing because we have to find it. We haven't run it yet. We need a subs run. Now, subs run is going to be real simple. We're going to do a subs invar of S. No, this is actually a very critical, very performance critical piece of function. So we're going to just assume the invariants are met. We'll check that in the testing, but at runtime, if you blow up subs, you've blown up subs. Okay, there we go. Remember, subs run is actually getting an address. List is an array of the structures. So this is actually type correct. And now we're calling stubs run, and it's actually doing this. And there's post. Okay. Now, is that the work I want to do during post, or is that the work I want to do during BIST? I think I want to do that much work during the built-in self-test and do less work in post. We'll only do one function here. Like that. So both of these are now getting executed. We saw them printing out before. I probably don't need to do them again. Actually, for built-in self-test, I'll also want to run it more than once. So I'll run it 3 times. Okay, there we go. Now for bench, I want to do something that's substantially larger. I'm going to set up a list it's larger than what I would normally do in the simulation. Let's see. Well, let's make it tunable, but I'm going to start out with 16 of them. So we need 16 things added to the subscription list, which take 16 different arguments. And when it's all done, we need to tear it down. But I can't statically initialize it because I don't know how big it is. So it can be dynamically allocated and freed. So int okay, old school again. If you can't remember how to use a function, you bring up its man page. So this is calloc of number of members. And inside that is the size of the thing. Plain assert, because if malloc fails at that point, if calloc fails at that point, forget it. When we come to that line, it's like, oh, yeah. We're going to start these at 0 this time. I'm still going to use a start val, but totally unnecessary since calloc 0 fills it. No, let's just do it based on. No, because the. Okay, so the benchmarking doesn't have a thing that we call before the benchmarking loop. It just says call this function a bunch of times. So I'm not going to be able to test how much the value changed in subsarg, so it doesn't really matter. Let's just make this unsigned. So nobody is tempted to think, oh, there's an overflow, integer overflow, evil, evil, evil. It's initialized to 0. What we want to do is add all the appropriate functions. We're going to use fn1 for them all. And this is going to be, say, p subs. Oh, wait a minute. I don't need p subs here. What I need to do is do a subs add. So for int I equals 0, I less than test len plus plus I. We do a subs add to s of the function, which is subs fn1, and the parameter is subs args plus I. Okay, now for benchmarking. Whoops, didn't mean to do that. So here, This isn't bench step, it's bench subs. And the function I want to call is subs run, and the parameter I want to pass to it is s. So I'm going to give the time it took to do the subs run, and then I'm going to give the amortized time it took for me to call each of the things on there. The second one should be approximately equal to the step run call. And I'm not calling the same thing over and over and over again. It's not going to be approximately equal. There's more things happening. Yep. Because before it was call, 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 and this is call in a loop. Also, I believe that we are doing a little bit more work in our function than we were in this. Let's check this. Step bench was doing step args. Okay, these were doing an increment. Okay. So I'm not sure why this is twice as big, but still, we're still down around 1.5 nanoseconds, so this is still incredibly fast. I probably want to put who is being benchmarked here. Oh, this is good enough. RTC, steps, subs run, StepAt. So, if the simulation really does have an edge, well, it has a thing that is running, and it has a list of other things it wants to call. Having that list of other things encoded in as calls is going to be faster than having an array of function pointers to call. That makes sense? Among other things, if it's an array, you have to go to memory to get the pointer, and then you have to go start fetching at the pointer, which means you are blowing any pipelining in the processor out of the water because you're fetching some address from memory. And you can only prefetch that so far ahead. So there we have it. We have, what do we have here? Check the invariants. Initialize the list, add entries to the list, run the list, post mist and bench of the list. So subs run with 16 entries on it, 21 nanoseconds. Now in the real hardware, that's 55 nanoseconds per clock edge. There's 9 of them. There's actually there's 9 of those times per cycle, per T state, and there's only 4 edges per T state. So we'd be using 80 nanoseconds to simulate 500 nanoseconds. Not bad. It's not all the work, but the dispatch costs are potentially the controlling cost in this simulation. Okay, so I am going to leave writing comments in here. I write documentation. I don't like to talk when I'm writing documentation. So I'm going to seal this up and commit it, and then we're going to start on the next thing. I thought I had a Kraken. Oh well. Let's use my shell for this. Checking, get status. Okay, so basically modified main step. Oh, let's do it here. Get diff. Okay, so in main, we added some things. And in step, we added step invar. We changed some names because having two things called step bench was a bad idea. And in step.h, we added that. And that's in addition to the new files we added. So we added subs.h and subs.c. We made those changes. Okay, and git commit -m add subs. So we're all set, and I have committed it. And if we go back, we look at git status. We're good. The build is turned off, so I could do a make clean and a git. So git clean leaves us with those files that are not deleted when you do git clean. That's okay. If I do a git clean, I may still want to see the standard error files. Or do I? Or do I? If I delete a file, git clean, make clean is what should remove it. So this is where it's made. So we're going to go down here where we remove the files that got made by the build. This is in log/cc-something.stderr. Come on. Okay, so this means that when we're done, if we do a make clean, the only files that make clean doesn't remove of are our Emacs backup files, which we don't want to remove automatically from the working area, and the result of the last run. I think I do want to remove that one. I think I want to keep that just like that. Let's refresh it. $C $less than is $inst. $at is this thing. I want to make sure I've got all of this set up correctly. Yeah. Okay. So down here we need a clean. Also does this. There we go. Okay, not going to push that yet. The next thing we want, we now have step and we now have our subs list. That gets us a whole lot of things we can do. In fact, we could do quite a big simulation using just those in combination with some bespoke logic that would basically set a signal low, set a signal high, set a signal low, set a signal high. But I think before I get into doing that, I wanted to set up two more data structures. One of them is called StepAt, which is a lot like step, but it has a scheduled time. So to do that, we start with copy step.h, copy that to StepAt.h. C does not have inheritance. So there's something called StepAt, which is going to look a lot like a step. I mean, a tremendous lot like a step, like the same code, except it will also have a scheduled time, and there will be some requirements around that scheduled time. Now, if you made StepAt a subclass of step, okay, if you used inheritance, and StepAt had any of the guarantees I want to make, then you will have violated the Liskov substitution principle, because there are some operations you could do on a step that if you do them on a StepAt, it's invalid. For instance, you can have a list of steps. If you have a list of StepAts, we're going to demand that they be in non-descending order. So there's StepAt, and we're going over here to StepAt.h. StepAt, and this is StepAt is StepAt. Now, some of our data types are going to be in common, so pound include step.h. StepAt AP is going to be the same thing as StepAP. So we don't need to define it. StepAt FP and StepAt FN are going to be the same. Okay, so we don't need to define them. So we have pStepAt and we have StepAt being defined this way, and I'm going to insert at the front of the structure a tau, which is at. Okay, so logs and format. So this is currently building. How about that? StepAt init is going to require one additional thing. It's called an at. So whatever numerical type you pass me, I'm going to cast it into a tau. You pass me a floating point number, I will discard the fractional part. Is that good? That's probably not good. I think what I need to do is use that so we don't get an automatic cast of our tau. So what do we have built in? We have from step, we've got the StepAt invariant. I am going to assert SAT is greater than or equal to the current time, which I'm going to have something called the current time, which is tau, which means StepAt owns a variable called tau. I'm putting it in uppercase because it's going to be terribly, terribly important. tau will represent the current time of the simulation, and every time we execute a StepAt, we will set tau to that time, and then we will assert that tau is never descending, okay? So tau will always represent the time at which the current step is running, or if a step isn't running, the most recent step had run. So we are not currently running any of the post or BIST or anything. Let's set that up. Okay, so I've been sitting here assuming that this has been compiling and the compile loop wasn't running. Okay, so here is what's actually happening. So StepAt.h. I forgot to include the thing for tau. Now StepAt init requires 3 arguments, but only 2 given, because I hadn't actually looked at any of this stuff. So we're going to start off with everything happening at tau 0, and then we're going to go back and work out what we need to happen. There we go. So StepAt run and step run should be about the same run time. There may be slight differences because the structures they're looking at are different sizes. Oh, and the run itself is updating a global variable. But we're not doing that yet, so we just say assert tau equals s arrow at. And I think it's worthwhile, at least initially, assert or is it? Nope, not worth it to me. StepAt run needs to be fast. We can update tau, but we really can't spend the time to do the comparison. How long is that comparison? So we went from 0.787. Okay, I'm wondering if that got elided. Nope. Okay, so I've noticed that when I was building under Windows, the release builds for Windows elide the contents of the assert. If I've got an assert, I always want it to be there. If I want something that comes and goes, I'll make that dependent upon a build parameter, because I strongly believe in test what you fly, fly what you test. So if your assertions are there in your final test, if the assertions don't get turned off with some tests still happening, if you don't test with the assertions out, then you shouldn't fly with the assertions out. Anyway, so we're not turning off asserts when we build for performance here. That is still plenty fast enough for the old man. So StepAt, it basically says you're going to run this StepAt, and as part of it, you're going to set tau to that time, and we're golden. We haven't checked to make sure that we're actually setting tau to that time, so we need to do that. So here we've got power on self-test. I'm going to verify that we advance to 5. So tau step is tau before equals tau, tau after is tau. Let's advance by 24. Oh, here's a place where I should have used assert EQ integer. There we go. Okay, so taking that away, we're not going to assert that tau is non-descending because we're doing too many weird things. A simulation that wants tau to be non-descending will arrange to have its StepAts happen in ascending order. Okay, so post now verifies that we are writing the expected value. Built-in self-test should probably do the same thing. Okay, so BIST, we've got 3 different tau values, and we assert when we are done that it's set to the last one. Bench, when we're using StepAts, these are generally going to be coming off of a heap. They're generally going to be inserted onto a heap. Their taus are going to be determined dynamically. I'm going to go ahead and use the same initialization. And bench StepAt is going to be at T0. So if we were going to be testing, if we're actually going to be doing any assertions about tau, then inside the test loop, when we ran back to start over again, we would have to clear tau, or we'd have to rewind tau, or we would have to set new StepAt values. Also, if we're going to repeatedly call a function that calls these StepAts, it would have to update the times in there, and that'd be an unfair burden. We don't want to test how long it takes to run a loop that includes updating those times. We just want to test how long it takes to run a loop that does the calls. So the StepAt runner cannot assert that it is always sending the tau. Okay, there we go. Now, because I am setting tau before I'm calling the functions know what the current tau is. If a function needs to manipulate a queue, it will have to have the queue inside its context area. And I believe that shows how when we get into the swing of things on this, and we're building a derived class, it's actually fairly quick. And I think that's StepAt. I mean, not that StepAt is anything important. I mean, it's a trivial change, but so the trivial change is not taking a significant amount of time for us to put together. Just to be absolutely sure. So confirm that we are running StepAt post, StepAt bist, and StepAt bench. There we go. So StepAt, the equivalent list, we got a subs, which is a subscription where you add yourself to the list, and then every time the list is run, you run all the subs. The equivalent for StepAt is a priority queue. And I am going to take a break at this point. I am no longer as sharp as I need to be to implement a priority heap. Basically, we're running in C right here. So we are implementing a priority heap from scratch. And I want to be sharp for that because there are edge conditions. It's easy enough to get off by one when you're looking at parents and children. It's easy to have edge conditions where you're not considering the first element or the last element of the heap properly. And the invariants get kind of tricky if you want to be invariant while a bubble is moving through the heap. You can do that. You can say, I have a bubble in the middle of the heap. And then you can say, is the rest of the heap properly invariant, ignoring any comparisons against that bubble element? You can do that, but I need to be sharp for that. So we are going to call it here. Is there anything else I want to seal up before I finish up with StepAt? That looks really weird to my eye. I expect to see step_at, but this is a method on the StepAt structure, so that's correct. I will get used to it. Oh, the other thing I wanted to do, we have established some new types. I have not been careful about adding them down to this list. So let's go through really quick. So step has the following types. Step has step and p-step, and oh, that's all the types it has. Oh, wait a minute. Yeah, step AP. Yeah, okay, we've got more. AP, FN, FP. So as I add these to this list and reformat, we're going to see these moving around. This, I would normally rate that indented like that, and I am not sure why. I'm not sure why this is not. Oh, there we go. So it's like sometimes it will extend StepFN back to the void and sometimes it won't. I think it's being confused by the fact that StepAP is out there. But Step and StepAt has all those same things. Except it doesn't have those. Those are shared. Subs actually was before that. Okay. Now, by informing indent that these are actual types, it means that, oops, dash T subs in lowercase is not a thing. There we go. By informing indent that these are actual types, there are some kinds of code where if it doesn't know that a word is a type, it won't treat it as a type, and you get strange indentation. It doesn't always work anyway, as we saw in step.h here, where I wanted to have StepFN be aligned at the appropriate point. I bet you if I put void star out there, no? I wonder what happens if I say void stepfp stepap. Eliminate stepn. Delete that entire. That actually looks better. Okay. Let's get rid of stepfn. Didn't need that anyway. Okay, so we're indented, we're running, we're passing our tests. We've got step, we've got subs, and we've got StepAt, and the next step is the heap, which I'm going to do tomorrow. So status is we've got some things that are changed. This is all part of StepAt. And I'm going to accept that as my add StepAt thing. Git add dot git commit dash m add StepAt. There we go. Oh, and there's Rob. He says, having your cam is nice. Yeah, I meant to turn that off. Yeah, I meant to turn off the camera. Probably because I left my monitor of all of that stuff behind other things. So you don't code behind your face. Yeah, and right behind my face is where I normally code. I will think about it. I think I could probably put my camera down the lower right-hand side of the screen. Okay, so let's move the camera. Move it down to the lower right. That is still, there we go.
Yeah.
Okay. So logging for the day, because I am not sharp enough to make sheep. I'll see you tomorrow.
Okay.
Gentlemen, it's been a day. Yeah, keep your code safe.